Hello, 11th graders. Today we are starting our last section of this unit. So to just kind of recap about what this whole unit was about, our very first lesson of this unit, I believe, was about coordinate geometry. So finding distances, finding midpoints, perpendicular bisectors, all of those things. And then our second and third lessons were about trigonometry. So the second one was about right triangle trigonometry. And then the third one, which is your law of sines, law of cosines, your area formula, those are all about non-right triangles. And so this is our last unit, our last lesson in this unit, and it's about surface area and volume. So just kind of capping this geometry unit together. So we're going to go through the formulas today and then have just one example. I'm trying to cut down on the length of your lessons, but we'll see how that goes because I talk a lot. So we're just going to be doing the volume and surface area formulas, and then we'll do one example, and then we're done. Okay, so these are your generic shapes you can see on your front page. These are your generic shapes that you'll be talking about. They all have formulas. Some of them are on your formula packet and some of them are not. So I'll guide you through which ones are on your formula packet and how to know how to do some of the ones that are not on your formula packet. Okay, so first of all, this is called a right square pyramid. It's called a right pyramid because the point of the pyramid, the vertex of the pyramid that comes up is at a right angle from the base, right? It's not slanted all the way over here. You don't have a pyramid that's going like this. You have a pyramid that's going straight up. So it's you'll see that it has like that little red square on the bottom by the base. That's why it's called a right square pyramid. It's called a square pyramid because the base is a square. So a triangular pyramid would be where the base is a triangle. So it'd be kind of interchangeable with all the other triangular faces of the pyramid, depending on where it's laying down. But here it's a square pyramid because the base is a square. The volume of this guy is 1/3 times the area of the base times the height. The height has to be perpendicular to the base. Thinking about like how you find the area of a triangle not using our trigonometry formula, just 1/2 times base times height. The relationship between your base and your height is that they have to be at a right angle. Area of the base, here it's a square, so you have to find the area of the square, and then your height is whatever that height to the vertex is. And 1/3, there's all sorts of fun ways to be able to understand why it's 1/3. But the main idea is that if you had a cuboid or a rectangular prism that had the same size base, that square was the same, and the height was the same, so it could be a rectangular prism, it doesn't have to be a cuboid. If the height is the same, if you filled up this rectangular pyramid with water and poured it into that rectangular prism that has the same size base and the same height, it will fit in exactly 3 times. So that's why it's 1/3. That formula, let me double check on I'm so fancy, I have so many computers. That guy, the volume of a right pyramid is on your formula packet. It is in your formula packet. It just has A, like uppercase A, not A of sub B, but this guy is in your formula packet. So I don't know if we want to like draw a star or something like that. Or like a check mark. Let's do a check mark to be like, yes, it is in your formula packet. Now, the surface area is not in your formula packet. The surface area you have to think about as all of the surfaces together. So finding the surface area, it's like every single face, every surface of that pyramid has to be broken apart. So what it is, it's not a very helpful formula because you have to visualize it. Surface area equals the area of the base plus the area of the triangles. If I were to draw a picture of what a right rectangular pyramid looks like, you've got the base. This is called a net by the way. You've got the base here, so I'll put B for base. And then you've got little triangles that come out from all sides. If the base is a square, then that means that all of these side lengths are the same. And since it has the same height when you fold them back up, this guy has to be the same for all of them. Those 4 triangles are the same size. So you could just find the area of one triangle and then multiply it by 4. If it's not a square base, if it's a rectangular base, then 2 of the side lengths, like this side length and this side length, would be equal. And then this side length and this side length would be equal. However, their heights would all be the same still. But you would have 2 different sized triangles. And so having to keep that in mind. This is what we call the net of a 3-dimensional shape. That's what it looks like. But it's the idea of you're finding the area of the base and then you add all the areas of the triangle. So you're finding the areas of all of the surfaces and adding them together. You have to be able to visualize it. If you have a hard time visualizing it, we're going to practice. This guy is not in your formula packet. This is an idea, a concept. It's not really a true formula. It's this idea of like, hey, find the areas of all the surfaces and then add them together. It's not in your formula packet. Okay, volume of a right circular cone. It's called a right circular cone because the vertex is directly above the base at a right angle. You'll see that little red square at the bottom at the base. And then it's called a circular cone because the base is a circle. You could have an ovular base, so like an oval or an ellipse of a base, and your cone would just look like flattened a little bit. But for the most part, we're just going to be talking about circular cones. All right, the volume here is actually the exact same as a pyramid, which is kind of crazy, but it's because the only difference between a pyramid and a cone is that a cone has a round base and a pyramid has a angular base. In other words, it's like a rectangle or triangle or square, right? All of which have corners, versus a cone has no corners or infinite corners, I guess, depending on how you look at it. But the volume here follows the same pattern. It's a third because if you were to fill it with water and dump it into a cylinder that has the same sized base and the same height, it would fill in exactly 3 times into a cone of that specific shape. 1/3 area of the base times the height. Now, the area of the base, it is a circle. And how do you find the area of a circle? Area of a circle is pi r squared. So in your formula packet, which I believe this is in, it is in your formula packet, and you'll see it's 1/3 pi r squared h, but it is just really the area of the base times the height. Okay, surface area. I'm going to first start off with drawing the net of a cone. If I were to ask you to make a cone with a piece of paper, or like a funnel or something, I'm sure you've done it before. Here's just like my scrap paper, but you would like wrap it around like this, and then you would have some sort of like thing that would cut through here to make it flat on the surface. But you've got this idea of like wrapping something around to make a cone such that the base becomes a circle. So I'm going to start with the base here. So the base is a circle, and then the net is really kind of a weird idea. But the idea here is that the lateral surface, it's called lateral because it's the sides of it. So the side surface is actually, let me draw that better. It's a part of a different circle. Imagine that the point goes to the center of the circle, but it's a sector of a circle. We haven't talked about sectors yet in this class. We will in our next unit, but it is this like part of a circle. And this part of the sector is the circumference of the base. Those guys are the same measurement. So that's the idea of the net of a cone. It's really crazy. So we're trying to find, with surface area, the area of all of the surfaces. So it's going to be SA equals the area of the base plus the area of the, on your formula packet, they call it the curved surface. So I guess I'll curved surface. That's a lot of words to put in subscript, but that's the idea, is you're finding the area of those two surfaces and adding them together. Now, area of a base is pretty straightforward. It's a circle, so as long as you can remember that the area of a circle is pi r squared, which, hey, by the way, I'm pretty sure that's on like your second page of your formula packet, is an area of a circle. So I do think that's on your formula packet as well, just in a different spot than your geometry formulas. Your other geometry formulas. So this is the area of the base. The area of the curved surface is on, so this guy is on your formula packet, but just that guy. So you have to realize that you have to add that guy, which is pi RL. And I'm pretty sure in your diagram, L is S. A little side note, L equals S. L is lateral height, and for some reason in this diagram in your textbook, they called it S instead. But in your formula packet, they call it L. So just be aware that L is that lateral height, the slant height, and that's why they call it S in the textbook, is it's for the slant height, versus in your formula packet, they call it the lateral height. But it's not the straight up height, it's the one that comes in at an angle. So only the area of a curved surface is in your formula packet. So you still have to think about the idea of a cone is the circular base and this like sector of a whole circle, and you're finding the area of both and you're adding them together. And that's your formula for the surface area of a cone. That's probably one of your more difficult ones. So don't worry, it's not going to keep getting harder. Actually, it's going to get easier from here.